Hello everyone, welcome to physics class. This is the second lecture on electrostatic potential and capacitance. In the previous class, we have defined electric potential. Electric potential at a point in the electric field is defined as the work done in moving a unit positive charge from infinity to that point against the electrostatic force. And this work done is independent of the path followed. Mathematically, we can write V is equal to W infinity B divided by Q naught. And also we have the SI unit of electric potential is volt or joules per coulomb or Newton meter per coulomb. The commonly used one is volt. I told you to define 1 volt. Electric potential at a point is 1 volt if 1 joule of work is done in moving 1 coulomb charge from infinity to that point in the electric field. This is the definition of 1 volt. Now, already we have seen that electric potential and potential difference are scalar quantities. That is their benefit. Electric potential at infinity we have taken to be 0. Now let's calculate the potential due to a point charge. For that purpose, we'll consider a point charge Q. Our aim is to find the potential at a point P, which is located at a distance r from the point charge Q. So for that purpose, we have to calculate the work done to bring a unit test charge from infinity to the point P against the electrostatic repulsion offered by the charge Q. First, let's calculate a small work done dW in order to move a test charge Q naught by a distance dx. And to calculate the total work done, we can take the help of integration. So we'll take point A and we will place a test charge Q naught at this point A. The point A is located at a distance x from the charge Q. A test charge Q naught is placed, it will experience an electrostatic repulsion Fe. Now we are going to move the charge from A to B by applying an external force, or we will move the charge by a distance dx with the help of an external force F external. For this, the work done dW will be F dot dx. So the total work done we can calculate by integrating this dW, that is infinity integral dW. So the total work done in moving the charge Q naught from infinity to the point P will be W is equal to integral dW. This will be equal to minus integral infinity to R Fe dx. The minus sign indicates that the work done is against the electrostatic repulsive force Fe. We already know the expression for Fe, that is given by 1 by 4 pi epsilon naught Q naught divided by x square. It is the electrostatic force between two charges Q and Q naught separated by a distance x. If you substitute this value Fe in the integration, we will get W is equal to minus integral infinity to R 1 by 4 pi epsilon naught Q naught divided by x square into dx. In this, the variable is x. All other quantities are constants, so we can take them out of the integration. So W will be equal to minus Q naught divided by 4 pi epsilon naught into integral infinity to R 1 by x square dx. We know the standard result integral 1 by x square dx is minus 1 by x. So this will be equal to minus Q naught divided by 4 pi epsilon naught minus 1 by x. R is the upper limit, infinity is the lower limit. Now let's apply the upper limit and then subtract the lower limit value. So we'll get minus Q naught divided by 4 pi epsilon naught into minus 1 by R minus 1 by infinity. 1 by infinity is 0, so simply we are left with minus 1 by R. Minus and minus becomes plus, so we will have the answer W is equal to 1 by 4 pi epsilon naught Q naught divided by R. This is the work done to move a unit test charge Q naught from infinity to a point P. From the definition of potential, we know that potential is equal to work done per charge. So W is equal to 1 by 4 pi epsilon naught Q naught divided by R. Therefore, the electric potential at point P is given by V is equal to W by Q naught. W is 1 by 4 pi epsilon naught Q naught divided by R and divided by Q naught. In this case, Q naught and Q naught cancels. So we will get the potential at point P to be V is equal to 1 by 4 pi epsilon naught Q divided by R. This is the electric potential due to a point charge Q at a distance R. We already know the electric field value at a point R from the charge Q, that is 1 by 4 pi epsilon naught Q divided by R square. If we compare these two expressions, we can see that the electric field intensity varies inversely as the square of the distance and the electric potential value varies inversely as 1 by R or proportional to 1 by R. So if we plot the graph between the distance, electric field intensity and potential, you can see that the electric field intensity is steeper. The graph of electric field intensity is steeper than the graph of potential because E is inversely proportional to R square, but V is inversely proportional to R. Next, let's find the electric potential due to a group of point charges. Since electric potential is a vector quantity, in order to find the total potential at a point due to group of point charges, we have to simply add them. So we will take a point P and we will place a unit positive charge there. So let's imagine that around this charge we have the charges Q1, Q2, Q3, Q4, etc. Qn. There are n number of charges around this charge or around this point P. Our aim is to calculate the total potential at point P. Let the distance from the point P to charge Q1, Q2, Q3, etc. be R1P, R2P, R3P respectively. So the net electrostatic potential at a point in the electric field due to a group of charges is the algebraic sum of their individual potentials at that point. So we can write Vp, that is potential at point P, is equal to V1 plus V2 plus V3 plus V4 plus etc. Vn. We already know the expression for V1, V2, V3, etc. Vn, and you can write 1 by 4 pi epsilon naught is common in all these terms. So I can write it as 1 by 4 pi epsilon naught bracket Q1 by R1P plus Q2 by R2P plus Q3 by R3P plus Q4 by R4P plus etc. Qn divided by Rnp. If you write this expression with the help of summation, then you can write it as V is equal to 1 by 4 pi epsilon naught sigma I is equal to 1 to n Qi divided by Rip. In terms of position vector, you can write it as V is equal to 1 by 4 pi epsilon naught sigma I is equal to 1 to n Qi divided by R vector minus Ri vector magnitude. You can see the advantages of electric potential over electric field intensity vector. Here we have to simply take the algebraic sum, but in case of electric field intensity, you have to apply superposition principle or you have to add the individual electric field intensities vectorially. From these expressions, we can see that electric potential at a point due to a charge is not affected by the presence of other charges. And also potential V varies inversely as R, whereas electric field intensity E varies inversely as the square of the distance R. Now potential is a scalar, whereas electric field intensity is a vector. Now, although V is called the potential at a point, it is actually equal to the potential difference between the points R and infinity. Now let's find the electric potential due to an electric dipole. For that, we will consider a dipole. So it has two charges equal in magnitude, opposite in polarity, that is plus Q and minus Q. They are placed at B and A positions respectively. Let the dipole moment is represented by P vector and the center of the dipole is O. The length of the dipole is 2A. That means each charge is located at a distance A from the center of the dipole. Now our aim is to find the electric potential at point Q due to this dipole. So this is a general point. In case of electric field, we have taken two special cases, that is one along the point along the axial line, another point along the equatorial line. That was because the calculations involving vectors are complex. But in this case, electric potential is a scalar quantity, so the calculations are much simpler. So instead of going directly to the special case, we can consider a general case, and from that we will discuss special cases. So here I have taken a general point Q. So how to define this point Q? So this point Q is at a distance r from the center of the dipole, as well as one more quantity, that is theta. Theta is nothing but the angle the point Q makes with the axis of the dipole. So the point Q has two specifications. One is its distance, another one is the angle represented by r and theta. Now we have to find the potential at point Q due to this dipole. As we have two charges in the dipole, minus Q and plus Q, we have two potentials at point Q. And to find the total potential, you have to add these two potentials. So the first potential is due to plus Q charge, the second potential is due to minus Q charge. So first let's define the distance from plus Q and minus Q to point Q. So the distance from point B to Q is represented by R2, and from the distance from A to Q is represented by R1. So we have these many parameters: R1, R, R2, theta and A. Now first let us find the potential at point Q due to plus Q charge. So you can write the potential at point Q due to plus Q charge is 1 by 4 pi epsilon naught Q divided by the distance, that is distance from plus Q charge to point Q, that is nothing but BQ, or we can write it as R2. The second potential is due to minus Q charge. So it is located at a distance AQ, or the distance R1. So you can write the expression as 1 by 4 pi epsilon naught minus Q divided by AQ. Since these potentials are scalars, in order to find the total potential, you have to simply add them. So you'll get the total potential at point Q is potential due to plus Q charge and potential due to minus Q charge. So let's substitute the equation. You can see in both the equations 1 by 4 pi epsilon naught is common. 1 by 4 pi epsilon naught is common. So you can take also Q is also common. So the remaining term in first expression is 1 by BQ, in the second expression is minus 1 by AQ. So if you substitute that one, you will get BQ is equal to Q divided by 4 pi epsilon naught 1 by BQ minus 1 by AQ. And BQ and AQ can be written as R1 and R2 as we have discussed in the diagram. So you can write it as Q by 4 pi epsilon naught 1 by R2 minus 1 by R1. So if you cross multiply, you will get R1 into 1 minus R2 into 1 divided by R2 into R1. So you can write this one as VQ is equal to Q divided by 4 pi epsilon naught R1 minus R2 divided by R2 R1. Here one problem is there. We have defined the point in terms of R and theta, but we have two additional points here, distances here. They are R1 and R2. So our aim is to write the potential in terms of R, theta and A. We don't want to increase the unknowns. So let's write R1 and R2 in terms of R, theta and A. For that, what you can do, AQ has to be written in terms of OQ. But you can see that the lengths AQ and OQ are not equal, but you can find the equal length by drawing a perpendicular to the line OQ. So I am going to draw a perpendicular from point A to the line OQ. So first I will extend the line OQ and then I will draw the perpendicular and this perpendicular from point A will meet the line OQ at point C. Now since it is a perpendicular, you know that the distance AQ and CQ are equal. So here I have drawn the perpendicular from A to the line OQ. So what will happen? The distance, now the distance is CQ and AQ, both are equal. That means AQ is simply R1 is CQ. But from the diagram you can see that CQ is from here C to O plus O to Q. Or you can write C to O plus O to Q is nothing but R. Therefore C to O plus R. So I will get R1 is equal to AQ is equal to CQ plus equal to R plus CO. Now let's consider the triangle ACO. It is a right angle triangle and CO is nothing but the adjacent side and AO is the hypotenuse. What is AO? For the dipole it is nothing but A. Therefore you can write the adjacent side CO is equal to hypotenuse into cos theta, or simply AO into cos theta. AO can be written as small letter A. So in this expression, for CO, let's substitute A cos theta. So you can write R plus OA cos theta, or simply R plus A cos theta. So you got R1 is equal to R plus A cos theta. That means we have written R1 in terms of R, A and theta. Similarly, let's write R2 or BQ in terms of R, theta and A. For that, what is the first step? You have to draw a perpendicular from point B to the line OQ. So I have drawn the perpendicular and that perpendicular meets the line OQ at point D. Now we know the distance BQ and DQ are equal. So let's write BQ is equal to DQ. But what is DQ in terms of R? DQ, you know that the total distance from O to Q, it is R. So, but DQ is smaller than OQ, or you can write DQ as the total distance OQ minus this distance OD. So I am writing OQ minus OD. What you will get? You will get DQ. Or you can write R2 is equal to total distance is R minus the small distance is OD. So you can write R2 is equal to BQ equal to DQ equal to R minus DO. Now let's consider this triangle. Here you can consider the triangle. This triangle is nothing but ODB. Here OD is the adjacent side and OB is the hypotenuse. So as I told earlier, the adjacent side can be written as hypotenuse into cos theta. So in this case, OB cos theta. OD is equal to OB cos theta. What is OB for the dipole? It is A. So you can write A cos theta. So you will get R2 is equal to BQ is equal to DQ is equal to R minus DO equal to R minus OB cos theta. That is nothing but equal to R minus A cos theta. So in this expression, we got R1 and R2. R1 is nothing but R plus A cos theta and R2 is R minus A cos theta. In the next step, we will substitute these expressions for R1 and R2 in this equation. We have the previous expression, that is VQ is equal to Q by 4 pi epsilon naught into R1 minus R2 divided by R2 R1, and from our assumptions we got R1 is equal to R plus A cos theta and R2 is equal to R minus A cos theta. Let's substitute the values in this expression for R1 and R2. So in the numerator we will have R1 minus R2, that is R plus A cos theta minus in the bracket R minus A cos theta. So R and R cancels. So we'll have A cos theta minus A cos theta. That is nothing but A cos theta plus A cos theta, which is 2A cos theta. In the denominator, we have R1 into R2. That is R plus A cos theta into R minus A cos theta. That is R square minus A square cos square theta. So the expression for the potential at the point Q becomes Q divided by 4 pi epsilon naught 2a cos theta divided by r square minus a square cos square theta. See the denominator, you can see the term q2a. Q is the charge, 2a is the distance of the dipole, length of the dipole. Q into 2a is nothing but the dipole moment. So you can write the potential at the point VQ as 1 by 4 pi epsilon naught P cos theta divided by r square minus a square cos square theta. This is the general expression for the potential at any point Q which is located at a distance r from the center of the dipole and making an angle theta with the axis. Now let's take the two special cases, that is axial line and equatorial line. First we will consider a point Q lies on the axial line of the dipole. When it is the axial line, you can see that the angle theta will lie on the axis. Therefore, the point Q lies on the axis, therefore the angle theta becomes 0. So when you substitute theta is equal to 0 in the expression VQ is equal to 1 by 4 pi epsilon naught P cos theta divided by r square minus a square cos square theta, the cos theta terms cos 0 becomes 1 and cos square theta also becomes 1. So you will get VQ is equal to 1 by 4 pi epsilon naught P divided by r square minus a square. And for a short dipole, A is very much smaller than r, then we can write VQ is equal to 1 by 4 pi epsilon naught P divided by r square. This is the expression for the electric potential for a short dipole at a point Q which is located at a distance r along the axial line. Now, the second case in which we will take the point Q lies on the equatorial line. So if it is the equatorial line, the angle theta becomes 90 degree. So you will get cos theta is equal to 0 or cos 90 is 0. Therefore, the potential along the equatorial line. So in today's class, we have discussed the electric potential due to three charge configurations. First one, the electric potential due to point charge, then group of charges, and then electric dipole. So first we have seen that the electric potential due to a point charge is given by V is equal to 1 by 4 pi epsilon naught Q divided by R. If we have group of charges, we have to simply add them algebraically and then we will get V is equal to 1 by 4 pi epsilon naught sigma I is equal to 1 to n Qi divided by RIP. In case of an electric dipole, we have the general expression at any point Q which is located at a distance r from the center of the dipole and making an angle theta with the axis. We have the expression VQ for electric potential is equal to 1 by 4 pi epsilon naught P cos theta divided by r square minus a square cos square theta. And in the two special cases, one is along the axial line, we have the expression VQ is equal to 1 by 4 pi epsilon naught P divided by r square, and if the point Q lies on the equatorial line of the dipole, then VQ is equal to 0. So that is for today's class. Thank you.